Hi, it's Joe Menchevsky, the host of Better Buildings for Humans. This is a series of conversations with thought leaders about indoor environmental quality. We're going to talk about daylight, views, fresh air, and thermal comfort, and so much more. These conversations are for architects, designers, engineers, building owners, people who care about the comfort, health, and productivity of the people who work, live, and play in their buildings. Come join us if you want to be a part of the conversation. Recently, I got the pleasure to speak with Dr. Michael Kent. Michael's a researcher in Singapore, and he's associated with the University of California at Berkeley. He's a world-leading expert on daylight and views and their impact on humans. He's done some really interesting research on the negative impacts of glare from both artificial light and from daylight. It's an amazing topic, and I have to admit, I didn't fully realize how deep that rabbit hole goes. Michael's well-spoken. He's very passionate about his work. Now listen to this conversation if you want to gain a better appreciation of the importance of view and daylight and the ways in which glare impacts our ability to perform complex tasks. Let's dive in. First of all, why don't you tell us a little bit about the kind of research that you do?
Yeah, my pleasure. So my research basically looks at how light can be designed into buildings and also how people experience this light on an everyday basis. So predominantly, a lot of my work is motivated, I guess, by this famous quote, which often gets thrown around in the lighting research community, which often says that, there's more to light than just vision. And I've often felt from, that perspective, it's important to understand how light influences other things, such as, human health, comfort, and also behavior. And also, if you expand that even more broadly to like energy and sustainability. And I think what this creates is like a very interesting dialogue and a lot of interesting challenges, which I often try to tackle within my own research. And often I've had the pleasure of like exploring these types of things for research in things such as exploratory laboratory experiments, in field studies, as well as like computer simulation. Mm-hmm. And also as well, like more recently, like newer and existing kind of methodologies such as like virtual reality. So in a broad terms,
would you repeat that, Michael? I'm sorry.
Yeah, so studies that are like in laboratory experiments, field studies in actual office buildings, computer simulations, and also as well like these new kind of emerging methodologies which we're now using in the lighting community, such as like virtual reality.
Gotcha.
Yeah.
Right. Okay. Michael, I didn't ask you this at the beginning, so I'm going to ask again. Could you tell us where you work, where you do your research, and what organizations you're associated with?
Sure, no worries. So at the moment, where I am right now is in Singapore. So if you're not very familiar with Singapore, it's in Southeast Asia. Mm-hmm. It's about 1.6 degrees north of the equator, so right on, near the tropics. So it's characteristically is very hot, very humid all year round, even at nighttime. So kind of lovely weather to go out at nighttime. When the sun's out, wear some sunscreen to be on the safe side. But I work here as a researcher. So for an institution, a technical nonprofit research center called the Berkeley Education Alliance for Research in Singapore. So it forms the acronym BEARS. And this is essentially a collaborative center which forms a collaboration between three main institutions. So the University of Singapore, NUS in Singapore, NTU, Nanyang Technological University, which is also in Singapore. And the third is the University of California, Berkeley. And together, we have professors, researchers, in this research center tackling all sorts of research that pertains to the built environment, such as, for example, thermal comfort, indoor air quality, acoustics, and obviously on my side of things, where I fit into the equation is indoor lighting.
Okay. Yeah, terrific. So, as you know, our world is a little more oriented towards natural light versus artificial light. How much would you say is there overlap with natural light and artificial light?
I think fundamentally, if you look at the pure physics, I remember Peter Boysen, who was like the former technical editor of Lighting Research and Technology and kind of one of the big pillars of lighting, often kind of arguing that, fundamentally speaking, they're both the same thing. So, at the end of the day, it's electromagnetic radiation within a visible spectrum. But there are nuanced differences between the two, such as, for example, like the most obvious being that daylight is dynamic. It varies, in its intensity, direction, color, timing throughout the day. And, that really is what kind of separates the two apart from each other. But fundamentally speaking, they're the same thing. We're sort of trying to design them into the buildings in the same way to make sure there's enough of it so people can see, they're comfortable, they can do their tasks. But, daylight has that dynamic component to it. And I always feel like that dynamic component is obviously what makes people prefer it over electric lighting. So there are differences, there are some similarities. Depends on, we can spend a whole different conversation on this, what those are. But I think that's probably the easiest way to kind of surmise, how the two kind of, if we contrast them together, I think that's how I would summarize it.
Okay. How important do you think daylight is to building occupants?
I think it's incredibly important. So, for example, we know that people spend, about 90%, maybe even more of their time inside buildings. But as human beings, as we are, we're not designed to be encased in buildings. So, if we spend a lot of time inside buildings, particularly those that don't have good daylight access, or, this can actually have a lot of negative consequences on our health and well-being. So having good daylighting, having good daylight access into buildings is incredibly important.
Fantastic. So what would you say are the biggest challenges in bringing natural light into a building?
The biggest challenges. So the biggest challenges that I've kind of learned or kind of experienced so far have probably been to kind of bring natural light into a building while maintaining a good balance between, potentially conflicting design requirements. So I kind of feel like we're at a point now where design, research, and practice are sort of like at a point where we know how to bring natural light into the building, both in terms of like its quantity, timing, and other seminal design criteria. I kind of feel like this is sort of reflected in our building standards and guidelines. However, I think bringing that natural light into a building without sort of compromising other building design requirements is not as straightforward. And I think that kind of conveys with it other challenges. So for example, like if I take Singapore, which is a hot and humid climate, bringing natural light into the building is not so simple when you can easily overheat that building, causing other problems such as like thermal discomfort and high energy cooling demands. On the other end of the spectrum, obviously, we can bring the light into the building in colder climates, such as, for example, the UK, where I'm from, or potentially like some places in Canada. And this is very beneficial for solar heat gains, reducing heating loads. But at the same time, we've got to avoid things such as like glare from a low-hanging sun in the winter months. So I think these types of problems, I think if you bring them back together, these very different examples. I think what connects them all together is this idea of having a good balance between multiple design criteria, and obviously that's where daylight also fits into the equation.
Cool. Let's talk about some definitions, some things that not everybody might understand. The difference between disability glare and discomfort glare, which is I've never heard the term disability glare until very recently, till I read one of your papers. I think it's important for people to understand that there are differences. And maybe you could describe those for me.
Sure, yeah. So the difference between disability and discomfort glare is that disability glare will reduce our ability to see and discern visual objects. Hence, it's the glare that disables vision, while discomfort glare does not. So I've done experiments showing that even at high levels of discomfort glare caused by a light source, there's very minimal reductions in our ability to see and recall letters and numbers. I think it's about about 2%, for example, and that's really kind of what the main difference between the two are. If we go a little bit deeper on the research end, generally speaking, we sort of know the mechanisms of what causes disability glare. So we can kind of design it out of a building much easier because we can predict it and model it. We sort of know what lighting conditions cause it. While for discomfort glare, we don't. So there's a lot of sort of uncertainty behind a lot of the prediction models that we have. And it's sort of a sensation that happens in the building, which we don't really fully understand just yet. But there's a lot of research, obviously, in that area, obviously trying to characterize it a little bit better.
Yeah, and we'll expand on that a little bit. You made the comment that we know where disability glare comes from. We know how to predict it. Could you very briefly summarize the source of disability glare and how maybe even quantify it for us?
Yeah, so disability glare, I mean, it will tend to come from very bright light sources, and
Right.
that has a very direct light beam. So, obvious example could be from the sun, where a light beam goes into the eye, it scatters within the eyeball itself, and it causes like revealing reflections all over the retina. And obviously, when this happens, you can no longer see what you're looking at. So those types of things, I mean, we can sort of pinpoint scenarios that potentially could occur in a building, either by, like, for example, just being on site, looking up, when direct sun might necessarily appear, or we could just do this in a computer simulation. In hindsight, we don't have, the building, constructed at that point. So there's kind of other ways of doing it. And, as well, there are equations available. So I think if you look at some lighting standards, I noticed that there's some available there. So like the equations are relatively straightforward to calculate that. It's just, just basic photometry. We just measure these quantities that we need, just calculate it. We were able to get a decent measure of disability glare, so we can measure it, when we need to.
Okay. Oh, that's fantastic. I assume you see both in buildings on a regular basis. It's a common thing to see both.
Yeah, both can also, as well, and an important note, both can actually happen at the same time. So it is possible to get disability glare that's also discomforting. So they simultaneously appear. Obviously, it creates a whole new problem, which is very difficult to disentangle, but it is possible, in case anybody's asking or curious about that too, that the two can simultaneously happen.
Yeah, no, that makes a lot of sense. You've done some really interesting research that links building occupant performance with glare, discomfort glare specifically. Research focused on glare from artificial light, but does that translate to natural light as well, to sunlight?
Yeah, that's a really interesting question, actually. Yeah, so I would say that there's some parts that are transferable. So if you go from artificial lighting and then you transfer that knowledge into a daylit setting, then some of it is transferable, because it's, similar mechanisms, similar sensation occurs, it's uncomfortable. We sort of know that. But unfortunately, not everything is applicable. So there's a really interesting study done by Hopkinson in the 1970s, which sort of showed like the original glare index that he created for artificial lights, and which was applied to daylit windows. And generally what he found was a very similar trend between, observed data that was plotted, his glare index formula for artificial lighting against how people felt. And what Hopkinson noticed, although that you have this similar trend, there's actually this consistent overestimation of what people actually felt compared to what his glare index was telling him. So in other words, the glare index was showing that there was more glare than what people actually reported. And what he hypothesized is that there was something present, obviously, for these daylit windows when the glare was present, which was not present when he was measuring it just for artificial windows. And what he deduced was that actually this was the window view. So this is something that the window has, which obviously electric light doesn't. And this was actually later confirmed by research in 2005 and 2007 by researchers in the UK, showing that actually windows with a better view increased people's tolerance to glare from a window. So having that in mind, you can actually see how the two are actually kind of independent from each other. So in that sense, not everything is applicable anymore.
Right. That is really interesting. Yeah, we speak often at Advanced Glazings about the importance of daylight and view, connect anything that connects occupants to the to the natural world. But it's interesting that ensuring that there's some quantity of decent view. And we'll come back to view a little bit later. But it's interesting that glare becomes more tolerable when there's view associated with it. That's that I did not know. The glare index, I'm going to dive a little bit on that one. How much of a role does contrast play as opposed to absolute brightness?
So that's another really good question. So if you're looking at a small source, so let's say like an electric light, for example, that small source. So if you look at the contrast between it, so you take the brightness of the glare source, if the electric light is causing glare itself, then obviously the contrast will be very important because the glare source is small. So then the background will be much darker because it's less affected by the source itself. And that's obviously reflected in a lot of glare index formats, such as like the unified glare rating, for example. That takes a contrast term, and obviously that's how we measure glare for small electric lights. But if the source is much bigger, so if we look at the daylit window, then obviously the contrast effect is less important because the source is much larger. It affects the background illumination. So obviously the contrast term plays a less important role. And what we have now is like formula such as the daylight glare probability, which is used for daylit windows, which looks at, for example, a saturation effect, so like the overall brightness effect in the person's field of view, which it uses the vertical illuminance in lieu of the contrast term because it's much easier for people to measure that. It's just a spot point measurement on site that you could use, for example, or by simulation, it's actually much easier to actually use that vertical illuminance term instead. So yeah, so at the core of this, it just really depends on the size of the source. So it's small or it's large, then you know if it's contrast or if it's not contrast.
Okay. Oh, that's fantastic. Okay, that's good. Let's talk a little bit about the location of the illumination source. There was a quote in one of your papers, which was, I believe, a quote that you took from is it Iwata and Takura, if I'm pronouncing that correctly. And it says the source, a source of illumination placed above the fixation point triggered a lower level of visual discomfort than the same source positioned below the line of sight. Can you explain that and maybe elaborate a little bit on the implications of that?
Yeah, sure, of course. So if a glare source is sort of located above like a fixation point, or put simply, is basically what the person is currently looking at, this actually will cause more visual discomfort than if it's located, if it's located below, it will cause more visual discomfort than if the source was located above it. So in other words, if I'm looking at the computer screen right now and there's a glare source below the screen, that would be perceived as being more uncomfortable than a source of a comparable brightness and size that's located above the same screen. The reasons why this happens, I don't know if it's entirely clear. I haven't managed to find a particular reason that pinpoints exactly why this occurs. But if I had to make an assertion, it would probably be due to our experiences and expectations for what glare is and usually where it occurs. So for example, glare typically occurs in a daylit sky or ceiling lights, which would usually appear in the upper part of the visual field. And obviously that's where we're usually expecting the glare source to be. The implications to how this informs daylight practice, I mean, probably like if we look at like how we design desk surfaces, I mean, that's probably one idea, I guess, that we could ensure that those surfaces, particularly if they're near a window, are not too reflective, so it doesn't bother people on a more regular basis. So that could be one application. I think designers could potentially figure out, other circumstances where this could be a potential problem.
Right. Well, there's one that comes to mind, and there's a reason I asked the question. A very common use of engineered light diffusers to bring light into a space is to have the vision glass at that sort of 3 feet to 6 feet kind of, or 7 feet kind of range, and then above that in like a transom type position, you would have is where you'd put the engineered light diffuser. Part of that is to get that light bouncing off the ceiling so that it remains in the visible light spectrum and pushes in a little bit deeper. But now when I read that quote, I thought, the position of the light diffuser up high, if you did have like direct sunlight that was causing glare, you could pull the blinds on the vision glass temporarily and leave the light up top, and you wouldn't experience the discomfort as significantly if it was above your line of sight. Is that logical thinking, or?
Yeah, I mean, it could be one particular application where, this type of scenario occurs. And obviously, if we look at the scientific evidence, quantify how likely is that going to bother people, we could look at it from obviously that spectrum, and obviously to say, like, is this going to be a problem, making informed decisions based off that research. I think that's sound reasoning.
Okay. Let's see. There's a correlation that you've discovered between fatigue and glare response, also between hunger and glare response. Are there? I'll ask two questions. The first one being, was that a surprise? And secondly, are there practical implications to those two findings?
So this was the research that I did for my PhD. So, back then we were sort of just like, I guess, measuring a lot of things. And obviously it was quite exciting time to do research because you were kind of new to it. Yeah. So I think the results itself are probably not that surprising because, if we kind of define what discomfort is, just in a very broad context, it's very subjective. So basically it's like whatever you feel right now. When we try to measure that, it's very subjective, which means also like it will vary from person to person. So like if you're more uncomfortable with something and you introduce something else that will start to bother you even more, like an irritant, so for example, hunger, or you're tired, you're more likely to feel more uncomfortable than somebody else who's, for example, not hungry or they're alert, they're more content, right? So I think on that kind of, from that perspective, I think the results are not necessarily that surprising. But informing this into architectural design, I've been asked this question a few times. I think if we try to propose very informed, practical implications for these particular findings, I think it'd be quite difficult. At least not in the same manner conventional standards convey across lighting design criteria. But what I think that these results start to do is that they sort of emphasize to researchers and architects, who we really are designing for, which are people. People are very complex. They have a lot of needs, and it's very difficult to bridge all those gaps. But having said that as well, I think there is an opportunity, at least, to consider other types of ways we can account for all those differences between people, like the individual differences that occur between different people and their needs and expectations. I think something that I think may already start to have been done, or at least I've been seeing it in other areas, is this idea of personalized controls or dynamic controls, which can better meet people's needs because everybody's different. There's no way of standardizing everybody. So if we're able to meet people's needs via things that they can control within the environment, locally or within the room itself, in some way, then I think that's a better way of handling these problems rather than the conventional methods of just creating one value that defines everybody,
right,
in an entire building or an entire country or across the entire world. So I think that's probably the best way to go about tackling this particular issue.
So there was something else in that research that I found very surprising, and that was that our tolerance for glare increases as the day progresses. Did that surprise you? Why do you think it's happening? And what are the implications of that finding?
Yeah, so that was the main question that was sort of came from my research for my PhD. And the motivation behind it was that we're well aware that light has a very profound influence on people. So it regulates a lot of physiological processes that vary on a 24-hour cycle. And this is basically what we refer to as circadian rhythms. And these rhythms also extend throughout the time of year. So like circadian rhythms, so like seasonal affective disorder, stuff like that come from this. So we know about these temporal effects. They're very well established within lighting. What we didn't know at the time, and I thought there were strong reasons to sort of connect the dots between all these points, was whether or not this sort of circadian-based effect also influence how we perceive glare. So, we don't perceive glare exactly the same way throughout the entire day. And when we ran these tests, we did the experiments. What we ended up finding is that people tended to tolerate more glare as the day progressed. And there was some evidence later on. So I remember speaking to some researchers in UC Berkeley later on, and they actually said there was a physical sort of explanation behind this, and it was sort of related to how the retina in the eye sheds its sort of outer layers, and it's more sensitive in the morning. So people are more sensitive to glare in the morning, and then as the day progresses, it becomes less sensitive, and that's why the tolerance may increase. So it's kind of nice to have that explanation later on, because as a background, I'm more of an engineer, so obviously I'm not going to go that far deep into the human physiology behind it. But obviously running these experiments and looking at it from a more practical standpoint, how we design for glare in buildings, I think it was nice to know that, like conventional metrics, basically don't take this into account. But, we sort of need to bear in mind that, as the day progresses, people perceive glare differently. It's not going to be the same for the entire time of day.
So would that have implications on, say, the amount of glazing you put on the east elevation versus the west elevation, or any other sort of design implications?
Yeah, for sure. I mean, yeah, because obviously that's where the glare will be experienced the most, for example, in the morning on the east, in the west, for example. So, I mean, it'll be difficult to sort of assign people into specific places based on how we characterize their tolerance to glare. Sure. But obviously that could be one way around it, particularly if that person's very prone, like they're very sensitive to glare. Photophobic people, as are often classified by. If they're very sensitive to glare and they're always shutting the blinds, and obviously you want to cure like the energy savings, for example, these things could matter. And so we could systematically or strategically assign people in desks based on the time of day, to avoid glare. Obviously, there's probably some design overlay onto this that needs to be considered. But once you apply these findings and obviously reap the benefits from them, that could be one way of going about doing it.
Oh, that's cool. Okay. Let's see, what else do I want to talk about? The glare index itself. Could you speak to the calculation of the glare index in more general terms, so that practicing architects, engineers, even building owners would be able to basically understand it?
Yeah, sure. So a glare index is essentially basically what it is a tool, and it's used to help prevent the occurrence of glare in buildings. There's also outdoor glare metrics, which are slightly different, but essentially they do exactly the same thing, but for things like such as street lighting and road lighting. But if we look at just inside buildings, those glare indexes, basically what they're defined by are four, basic measurement terms. So for example, the first one being like the brightness of the source, or the luminance of the source, the brightness of the background, so the surrounding brightness of outside of the source, the size of the glare source itself, and then the fourth term is its position within the field of view. And typically what you would find in these glare indexes is that the weighting and arrangements of these four terms are slightly different as to how they were sort of like constructed. They tend to come to a slightly different answer depending on the experiments that they were done. But you often find that they're embedded in most of these equations. So you can find them, and these weightings and arrangements are they're derived from scientific literature or lighting standards, and you can find them in there. And linked to every model, what you'll find is a semantic scale. And what this does is sort of describes either the probability or the magnitude of visual discomfort that the occupant will likely experience from the lighting conditions that are being measured by the designer or the architect. So when you calculate the glare index, you can then cross-reference, the glare index value that's calculated to these like semantic descriptors. And, you would then get a relatively easy interpretation, or I should say really easy interpretation of what that situation should be. So it would say, for example, it's uncomfortable. And in that circumstance, they can, rethink the design proposal that they have to, try to minimize that glare. And obviously they recalculate that glare formula again to see whether it's lower than that uncomfortable threshold, like an acceptable level. And obviously that would be then reasons, evidence-based, going to prove that, that lighting design is probably not going to cause glare during its operation.
Okay. Okay. Well, I'm going to change the subject entirely right now. We're going to talk about view. You were a co-author in a paper with Lisa Heschong and Stephen Selkowitz, and some of the heavyweights in that world, which I'm sure was wonderful to participate in. It took me down a really interesting rabbit hole. I didn't even know that this sort of research was taking place. But the paper talked about sort of quantifying, qualifying view in three categories: view access, view clarity, and view content. So would you mind speaking to each of those three, sort of parameters that define view?
Yeah, certainly. So a few years ago, we asked this question, what is view quality and how do building designers design for it? And generally what we found when we asked this question was that there was actually a lot of valuable resources available, from all parts of the world, which were trying to design for view, but just not all of it. So when we began to collect this information and consolidate it into what we have now is a comprehensive design framework, which then became the technical report, we actually began to realize that this information tends to fall into like one of three categories, which is the view access, how much people can see, how much of the view people can see. The view content, so basically is what they can see in the view. And the third one is, view clarity. So how clearly can the view be seen? And, all three of these things are very important to ensure good view quality. So that you can't just design for just one. So you could have very good view content, a very good view of like, a national monument with a clear sky, a lake, lots of nature. Good view access, so you're sat very close to a very large window opening. But if this thing is obstructed by shades of, for a predominant period of time because it has very poor visual privacy or a lot of glare, then that people won't be able to see through the view. So in the end, the overall view quality score will be low. And basically, that's what we try to do. So we were just trying to connect the dots here and create something that designers could, easily use to define a window view quality, just with three simple, rudiment terms like the content, the access, and the clarity.
What's the next step in that research?
So that's a very good question. So if we look at view content and view access, in terms of the scientific literature and the standards, I think that we're at a relatively good point where we can say that we know enough about them to know how to design for them within a view. So for example, a lot of green building certification standards, such as like the WELL, the LEED, BREEAM, they do a very good job in terms of defining what is good view access. It's very easy for architects and designers to design for that. Content-wise, we have some standards which kind of tell people what you need to have in the view so that it's good and it's appreciated by the occupants. So like, for example, water, nature, the sky, landscape, and the ground layer, all these things together, they make a relatively good view. But for view clarity, there's actually not a lot of literature, research, or even standards available that kind of quantify this very well. And it's sort of been the area that has been receiving a little bit more attention, particularly after we proposed this, view quality metric index. So that's what we're trying to do now is trying to better understand, what constitutes good view clarity and how can designers design for it in a building. And one of the biggest problems and challenges is obviously that the view clarity is actually dependent on the view content. So for example, like you could have very poor view content, but then the clarity won't matter. Or you can have a very particular type of view content, such as a very distant skyline, but you place a horizontal mullion bar right across it, which doesn't necessarily impact that much on how much you can see outside, but it completely destroys the view content. So obviously, there's nuanced things we need to account for this, which is not as straightforward. But obviously, this is the next steps that we're trying to take. So this is the next steps in terms of research that we're trying to tackle.
What about some of the newer technologies? Well, I guess they're not that new, but things like, say, electrochromics or building integrated photovoltaics. Is there any sort of research on how that impacts view clarity?
So we're doing that right now. So it's
Okay.
so the study results should be coming out relatively soon. We're doing that with artificial lighting as well. We're setting up some studies that do that also in Singapore, which is a very good candidate location to do it because Singapore has a lot of daylight abundance for the entire year. So looking at these technologies is very beneficial to see how it impacts view clarity. How we're going to go about doing that is quite interesting because it's not just, for example, how well I can see particular objects outside that quantifies view clarity. It's actually, for example, our vision is very much more complex. So it's seeing features in achromatic vision, so black and white and gray and all shades in between, but also as well through color, which is way more important for systems like chromatic glazing, which also tint the window, which obviously then changes the color, so it distorts things. So like, can we see the sky very well if the tint color is blue? Because obviously it's the same color. So obviously this is where we're sort of going in this direction, is looking at how does it affect view clarity overall, and obviously what parts of view clarity to human vision are being affected, and that's obviously where we're heading.
Oh, that's fantastic. Will you speak to me again? Is that research progressing?
Yeah.
Because I'd love to talk about that.
Of course.
Okay.
Of course, it's very exciting. We're excited to share this with other people as well to see how this could be potentially applied by them. Obviously, what we intend and what is sometimes being used for is not always the same thing. So it's obviously interesting to speak to industrial people like yourself to make sure that these things are being used, the way in which we intend, but what else we also need to do as well, because we don't necessarily cover everything that was important, although we would want to, but these talks are very important, obviously.
Absolutely. So, the series that this is part of, we call it Tech Tips for Architects. So let's step back to the big picture again. If you could give me 2 or 3 pieces of advice based on your research, practical advice for the architects, what would you say are some of the most important aspects of your research and how it impacts an architect's daily life?
So if I had to kind of just select specific things that I've done, I would guess I would probably select things that I felt had the largest potential to bring everyday changes to people's lives. So for example, like if I circle back to the stuff that I did on window view quality, we did a study 2 or 3 years ago now, which looked at, for example, the design criterion that supports view content within the European building standard for lighting. So I think it was the EN 17037 or something like that. And basically it has this criterion in there, which basically states to a designer that a distant content view is more beneficial for people. And generally speaking, what we did is we tested that criterion, design criterion, and it actually supports that. So generally speaking, if you have content and it's pushed further away from the view, it's more appreciated by people. But it doesn't apply to everything people see. So actually, because the criterion makes no distinction between if this is a building, or this is a really nice, nature or monument, for example, or blue space, for example, do people really want it to be seen very far away? So like, is this thing very generalizable? And I think because the criterion is relatively new, so I think it was only introduced in the 2018 version of the standard. It wasn't present in the one before. Obviously, there are things in there which haven't been fully systematically tested. So obviously, as a general criterion, it works. But obviously, thinking more deeply about this, we came to realize that, for example, if you have a very nice view of nature and it's very close to the window, obviously, that's a very good window view. But obviously, if you calculate the quality of that using this standard, we would say that it's a very low quality view. So obviously, as a designer and a researcher, obviously, these things are very important to consider. So I feel like there's some interpretation needed. And obviously, on our part as researchers is to try to inform those standards, because I think as a designer, they'll look at that view and this is a good view. So, but the standard doesn't agree. So obviously, this is where we're trying to push things forward. I think another study, which I think is a little bit different, a different topic, and something that I've done in Singapore, which I trying to look at is this idea of looking at ceiling fans and recessed lighting. So this was another interesting study we did a couple of years ago, and we showed that ceiling fans and recessed lighting, when you put them together, so ceiling fans are very good at saving a lot of energy, a lot of cooling energy, particularly in hotter climates. But with recessed lighting, it causes chaos. There's flickering, there's strobing, and also again, I look back at the standards, and a lot of these standards were saying just move them apart, and that's the problem solved. And it actually doesn't solve much, because the human vision is very complex because of visual parallax effects, the angle in which you see things. You can't actually get rid of flickering within a building if you have recessed lighting and these ceiling fans. And what we found is not only does it cause visual discomfort, it actually starts to impact on mental health, mental performance, and other parts of how we perceive the visual environment. I think the lesson that we learned from here, and sort of what I was trying to convey out, is that even though we have these technologies that save a lot of energy and are designed to save a lot of energy, it actually causes other problems in the building which you don't really want to do. So in this case, it was the flickering, and I think that sent out quite a powerful message, because obviously we shouldn't just be integrating these things and just saying from a thermal perspective everything's fine. But obviously, if you look at it from a daylighted designer's perspective, it's a bit of a nightmare, because there's people complaining about flickering, or they didn't necessarily perceive the flickering, they just get a headache, but they don't even know what's causing it. So obviously, looking at these things at a broader perspective, I've always found wanting to communicate this to architects, and see what they think, but obviously if they haven't been thinking about these things, it's nice to have this dialogue and conversation with them.
Oh, that's fantastic. I don't have any more questions. Actually, sorry, wait, I do have one more. I wanted to ask you how you heard of Advanced Glazings, how you came to even know we exist in the first place.
Yeah. So that's a great question. So I'm very active on LinkedIn. So I often post a lot of things on lighting. I share a lot of things. I post a lot of my research on. I post other things that people do, and usually I use a lot of hashtags. So I also hashtag like lighting design, lighting, daylighting, daylight design, anything along those lines. And and also as well, I search through the other people's hashtags which they put on there. And one day I just came across, because I was scrolling back, and I think this post came out maybe half a year ago by Advanced Glazings, and it was actually a very interesting post of ice rink, which was showcasing daylight design. I don't know whether it actually was exactly. I think it was like somewhere in Nova Scotia or something. And it's quite interesting because I grew up playing hockey, so ice hockey.
Oh, really? Okay.
So it sort of combined my love of two things, lighting and ice hockey. So I watched NHL. It's great for me in Singapore because the time difference means I can watch it, at a reasonable time out here, whereas when I was in the UK, I couldn't. But anyway, so combined those two things that I really love, and I was like, oh, this is interesting, because I've seen a few things. I've never seen any large scale projects, and this one was quite nice because a lot of the ice rinks I've been in, are predominantly artificially lit, because obviously in a sports arena, you don't want daylight glare appearing. It's difficult, and obviously as well, like the heat gains and stuff like that. But this was a nice design. It looked very well daylit, and I think in the post it said that there's no electric lighting on or something like that at the time. So it was quite fascinating. So I grew an interest there, and obviously I clicked on the link to the company and just started scrolling through what else was happening, and so it just went from there. So I think social media has a very powerful way of connecting us all.
Yeah, that's very interesting. Yeah, the name of the rink is Port Hawkesbury Arena. I'm in Nova Scotia. It's about 90 kilometers from where I'm sitting right now.
Oh wow! So, okay.
Yeah, I've been there many times. It's a beautiful feeling to walk into that facility.
It's amazing. I've been in a few ice rinks here in Singapore, and it doesn't feel quite right because it's so hot here.
Right.
And then there's an ice rink, so it's sort of it's great because I get to skate here and everything, but like it's kind of strange to be in such a hot place and there's ice rinks around. But anyway,
Thanks for listening. If you'd like to be part of the ongoing conversation about better buildings for humans, please subscribe and please share. Thanks again, and stay in the sunshine.